Now we define linearly independent vectors. So suppose we have a set of vectors. So definition. Definition. A set of vectors is called linearly independent. A set of vectors. Okay, the vectors are called to be linearly independent. Let's see, v1, v2, vn. The set of vectors is called linearly independent. If any linear combinations that sum this thing to a zero vector, if only if the coefficients vanishes. So this is the right side is zero, is actually we should write as zero vectors, but we just abuse our notation. Okay, then if this is zero, then this is equivalent to the coefficients, if only if the coefficients, all the coefficients vanishes. Okay, vanishes. For instance, example. Okay, the set I, j, k, they are linearly independent. Linearly independent. They are in different direction and they are not in one plane. Okay, so they are not coplanar. So for any linear combination, suppose if any linear combination xi plus yj plus zk is zero vector, then this tells us the coefficients x, y, z, they all vanishes. Okay. Okay, let's give one example that is not linearly independent. Okay, example. The set I, j, I plus j is not linearly independent. Linearly independent. Then we see it's linearly dependent. Okay, linearly dependent. Because here we can choose some coefficients. For instance, I plus j plus -1 times I plus j. You see, if we distribute I, subtract I, we get a 0, j subtract j, we get a 0. So the coefficient is non-zero, okay? So we have some non-zero linear combinations of the three vectors such that we get a zero vector, okay? Zero vector. So this means, so non-zero linear combination of these vectors are, we get a zero vectors. So in this case, we get linearly dependent vectors, okay? So when we use generating set, we can delete some vectors such that the remaining vectors are linearly independent. The remaining vectors are linearly independent, okay? Okay, so by definition, zero, example, zero vector is linearly dependent with zero vector is linearly dependent with any vectors. The reason is any multiple of zero vector, then we get again zero vector. Okay, so for instance, any vector v non-zero vector, for instance, and zero vector. So we can get any linear combinations. For instance, 0 times 1 then you get a 0 vector plus 0 vector, then you get a 0 vector. So the coefficient is non-zero, okay? Coefficient is non-zero. So that we get 0 vectors, 0 vector is linearly dependent with any vectors. Okay. Last time we also talked about compositions of composition of maps. So we define what a vector space is. I think the next thing is we want to study maps between these vector spaces, okay? So for instance, the rotation by power 2. Now, when we start studying real numbers, we talk about the functions, okay, functions. And then it's one-dimensional thing, function. And then when we study maps between vector spaces, because we have multiple dimensions, then we actually, the map becomes more complicated. So we should find the image of each base vectors, like what we get if we plug in I, what do we get if we plug in J, okay? So we should output the vector corresponding to I and then the vector corresponding to J for this rotation. Now, the image of the vector I, we write as the first column, okay, the first column of the vector A. And then the image of J, we write as the second column, okay? So we get a matrix, 2 by 2 matrix. And this, once we determine I and J, the image of I and J, X direction and Y direction, and then any other vector we can determine by X and Y direction. So this uniquely determine the rule for any other vector, okay? For any other vector. And then we can also define composition between maps, okay? Okay, today we will continue talk about this topic, maps between vector spaces. Okay, for instance, this example, rotation by angle theta. Rotation by an angle theta. Okay, rotation by angle theta. So an angle theta. Okay. Again, we are talking about the XY plane, the two-dimensional vector space. So suppose we have, this is X direction, we have Y direction, X, Y direction. Now, suppose we have the vector in the X direction I, okay? The unit vector along X direction I. And then we have the unit vector along the Y direction, which is, this is G, okay? So now if we rotate the thing by an angle theta, so suppose theta is here, so then we get, so this is OA, this is A prime, and this is OB, and then we rotate A, we rotated the vector, so I is the vector OA, okay? So we rotated the vector OA by an angle theta, then we get an, so rotation by an angle theta, then we get the vector OA prime, okay, OA prime. So what do we know about the vector OA prime? So how do we find the A prime, the coordinate of OA prime? Okay, here we have a unit vector, okay? If we rotate a unit vector, we again get a unit vector. So this is the A prime is on the unit circle. So we can determine this, the coordinate of A by the angle theta. So A prime, this X coordinate, we get a cosine theta. Y coordinate, we get a sine theta. Solving triangle. And then we get O OE prime, this vector cosine theta sine theta. Okay, cosine theta sine theta. Now this is the I. Okay, this is the I. Now G is the vector OB. If we rotate this by angle theta, then we get OB prime. Now, how do we find OB prime? OB prime. Now, if we rotate B by angle theta, rotate the thing by angle theta. Okay. So we get a B prime here. Okay, B prime here. Again, this angle is theta. Then we can find the coordinate of B prime. Now the coordinate of B prime. What is the coordinate of B prime? So what is B prime? Coordinate B prime. Coordinate of B prime is the x coordinate is negative. So it's negative direction, negative sine theta. Okay. Solve right triangle. Solve this right triangle. You will find the coordinate of a B prime. Okay. Solve this triangle. Let me make it bigger. Solve this picture. So the hypotenuse is OB prime, which is 1. Okay. Then then you can find the x coordinate and y coordinate of a B prime. So we find solving this triangle, then you find x coordinate and y coordinate of B prime. Okay. So the x coordinate is negative sine theta, the y coordinate is cosine theta. Then you can find the vector OB prime, which is negative sine theta, cosine theta. Okay, let's write in vector form. I.e., I is 0, 1, 0. We map it to, under this map, r theta, we map it to the coordinate cosine theta, sine theta. Okay, then the G is 0, 1. Map it to negative sine theta, cosine theta. So if you write as matrix, then you see r theta will correspond to this matrix. So the first column gives us the image of I. Okay, so it's cosine theta, sine theta. And then the next column gives us, the second column gives us sine theta, cosine theta. Okay. So this rotation with respect to, rotate this thing with respect to O by angle theta. Okay. Now what happens if we do this? If we rotate an angle alpha, and then we rotate an angle r beta. Okay. So suppose we have a vector xy. We rotate the thing by r beta. And then we get r beta xy. And then we rotate the thing again by an angle alpha. So get r alpha, r beta xy. Okay. And another way, we just directly rotate it by an angle r plus beta. Okay, so we can do addition of this rotation. Rotate an angle alpha plus beta is the same thing as rotate an angle beta and then rotate an angle alpha. Okay, so this is the clearly we can, this is the equivalent. So we should expect that the r rotation with respect to O by an angle alpha plus beta is the same thing as rotation of an angle alpha. So we first rotate it by beta and then rotate it by alpha. Okay. Now, if you do this according to the multiplication rule, the composition rule for matrix, then you see the left side we get, this is according to the rule. So we already know what this rotation looks like. So this will be negative sine alpha plus beta. This we get sine alpha plus beta. This we get cosine alpha plus beta. Okay, and then the right side we get two matrices. I think this will be equal. Okay, cosine alpha, negative sine alpha, sine alpha, cosine alpha. And then the matrix corresponds to beta. Then we get cosine beta, negative sine beta. Then here we get a sine beta, cosine beta. Okay, last time we talked about how we compose maps. Okay, how do we compose maps? Then we get a rule to multiply matrix. Then if you multiply the right side according to the rules that we defined last time, how do we multiply matrix together? Actually, we did it last time. So you can see we did last time where the rule is. We define it. So we have the rule to compose matrices. Okay, if we have the 2 by 2 matrices, and then we know how to multiply them together. Okay, by the composition rule. And then here we have this matrix, these two matrices. The right side we have these two matrices. And then according to the rules that we get last time, we can multiply these matrices, two matrices together. So what do we get by the rule that we used last time? The right side is, by the rule last time we obtained, then we get a cosine alpha cosine beta minus sine alpha sine beta. And then this side we get negative cosine alpha sine beta, negative sine alpha times cosine beta. And then this side you get sine alpha cosine beta plus cosine alpha sine beta. And then this side you get negative sine alpha sine beta plus cosine alpha cosine beta. So okay, you can check with the rules that we did last time. Now you see, then we compare the inches. So compare the inches. Compare the inches. What we find is, for instance, we compare the first row and the first column, entry of the first row and the first column. Then first row and first column. Then what do we get? The right side is a thing, the left side we get a thing. So we get, so these are the same. So we should, the entries should be the same thing. So we get a cosine alpha plus beta. We get cosine alpha cosine beta minus sine alpha sine beta. Okay. So we get addition rule for the trig. Sine alpha cosine beta plus cosine alpha sine beta. So this is the addition law for the trigs. Okay, so that to be short, the addition law of the trigs comes from the addition law for these angles. Okay, you rotate this thing, we can add the angles when we do rotation. Okay, this trig actually says this composition. You rotate alpha and then rotate beta is the same thing as rotate by alpha plus beta. So this is actually what implicitly this trig addition says. Okay, this addition law. Addition law for trig functions. Trig functions. Okay. Now we do a little further. Now you see, if we rotate an angle by theta, rotate this vector by an angle theta, then we can rotate it backwards. Example. So this is the x, this is the y. Last time we rotated the positive direction by pi over 2. Now let's rotate it by the negative direction. So rotate it pi over 2 is negative direction, negative angle. Then what we get? So it's a r negative pi over 2. Okay, negative pi over 2. Then you see where does the image of I and where is the image of j? This is I and this is j. Now if we rotate it by pi over 2, then you see the I will becomes, so the matrix, the vector I will becomes the negative direction of j. Okay, this is negative j. So this means I goes to, under this operation, I goes to negative j. And how about j? J goes to I. Okay, j goes to I. So negative j in coordinate form, this will be 0, -1. And I in coordinate form will be 1, 0. Okay, 1, 0. So this R negative pi over 2 will correspond to this matrix I, the image. The first column is the image of I. The second column is the image of j. Okay, so you check. Remember what is R pi over 2? R pi over 2 is this one. R pi over 2 is this one. So R pi over 2, you just how do we get R pi over 2? Rotation by pi over 2 direction. So you see, if we rotate the positive direction pi over 2, then you see I will goes to j. I goes to j, which is 0, 1. Okay, j is here. I goes to j, and j goes to negative I. Okay, j goes to negative I, which is -1, 0. Okay, if you put this, the first column gives us the image of I, which is j, 0, 1. The second column gives us -1, 0. Okay, so you check that. According to the rule of matrix multiplication, you check R negative pi over 2 times R pi over 2. This is actually R rotation by, negative pi over 2 plus pi over 2. Rotation by 0 angle means no rotation, which is identity, nothing changed. Identity matrix. Identity matrix with I. Okay, you can directly check that this gives you, according to the rule of matrix multiplication, that we get the identity matrix 1, 1, 0, 0. Okay, check this by the rule of matrix multiplication. Okay, matrix multiplication. Okay, so this actually, the identity matrix does not do anything. It keeps everything fixed. Okay, keeps every vector fixed. You can check that identity matrix 1, 1, 0, 0 multiply x, y. Then you get, so this is the identity matrix xi plus yj. The image, the first rule gives us the output of I. Okay, so xi gives us x the first column. Then yj gives us y column, y multiple of the second column. So this gives you multiplied by scalar. So this gives you x0. This gives you 0y. So again, you get xy. Again, get xy. You plug in xy, output is xy. So no change. So this tells us the diagonal term is y, and then all diagonal terms are zeros. Then this gives us identity map. Okay. Okay. So the vector, any vector, xy is fixed. Is fixed by I 0 y 0 0. Okay. So this means for any xy, for any xy. This means the matrix y 0 0. So this matrix that we did fix everything. So it's the identity map. Okay. So this means identity map. Fix everything, keep everything fixed. Okay. So you see, we have rotation here is invertible. We can rotate it by an angle, and then we can rotate it backwards. So this is recover the original thing. Okay. Now the composition actually gives us matrix multiplication. So composition of maps gives us matrix multiplication. And then for certain matrix, we get actually identity matrix. So the idea is composition of maps. Composition of maps. Of maps between vector spaces gives us multiplication rule. Multiplication rule for maps. For maps or matrices. Okay, so and maps gives us correspond to matrix. Map between vector space correspond to matrix. Okay, and the composition of maps gives us the multiplication rule for that's just multiplication of matrices of matrices. Okay, now you see some composition we can get the original thing is identity map. For instance, R theta and R negative theta. This is identity. So if we have two matrices, then definition. If given a matrix, this gives us a rule of maps. Given a matrix A, if there exists another matrix, a matrix B, such that we are talking about square matrix. B times A is identity. Then B is called an inverse. B is called a left inverse of A. Okay. Now if AB equal to I, then B is called a right inverse. A right inverse of A. Okay. Okay. Now the following theorem says if BA equal to I, i.e. B is left inverse of A, and we have another right inverse, B prime. Suppose we have left inverse B and we have a right inverse of A by B prime, then necessarily, then B equal to B prime. Okay, right inverse and left inverse should coincide. Okay, so this is easy to prove. Okay, so you see we B times A, this is I. We multiply both sides by B prime times B prime. This is actually equal to, remember, B times A is I. This is I times B prime. I is identity. Identity times anything, we get 1. Times we get it itself. Okay. On the other hand, we have association law for matrix multiplication. So we can write this thing as, okay, and then this is B times I, which is B. Okay, you see, we finally get B equal to B prime. We compute it in 2 different ways, and then we get the same thing. So we get B equal to B prime. Later, we will see that if a matrix is left inverse of A, then it is automatically a right inverse of A. Fact. If A and B are square matrix, and PA equal to I, identity map, then we have AB is also equal to I, i.e. a left inverse is also a right inverse, is also a right inverse. So we don't see left inverse, right inverse at all. We just see the inverse. So we just see because left inverse and right inverse is just inverse. Okay. So then we just see the inverse. Then we see B is inverse of A, the inverse of A. Okay. The inverse is unique if it exists. Okay. The inverse, if it exists, then it's unique. And then if A has an inverse, then we see A is invertible. If A has an inverse, has an inverse, then we see A is invertible. We see A is invertible. Invertible. Now, when we do some operation, natural question is, this kind of operation, is this operation invertible or not? Okay. If this operation is invertible, then we don't lose any information. We can recover it by just the inverse operation. So it's a really important question. When certain map is invertible, okay, when we can actually do the inverse, find the inverse, or the map is invertible. Question. When does a matrix or a map is invertible? Okay. This is actually an important question in linear algebra. Now, first of all, we do some very trivial thing to get some idea. For instance, functions. How do we define inverse functions? So for functions is map between sets. Okay. For instance, we have an object star. We have suppose we have objects. Suppose we have one bullet point. This bullet one, we have another object bullet two. They are distinct. Let's for instance, let's use star to mean they are distinct objects. Now we under a map, for instance, F, and a rule that we map it to this object star. Okay, so then you see the two objects map to the same object star. Then if we invert it, then we actually have to do choice. So F inverse star. Now we have two choice to make. Okay, whether it is the bullet point or the star. Okay, so we have to make choice. So this is not well defined. Is not well defined. Not well defined because we have to make choice. And one people may use one choice and another people may use different choice. So that's no universal conclusion. Okay, so it's not compatible. It is not natural. Okay, so we cannot define it uniquely, the inverse. Okay, so in this case, we have a multiple objects mapped to one object under the map F. So F is not invertible. Not invertible. The reason is multiple objects mapped to the same target. Okay, so in some sense, the two objects is squeezed to one object. Okay, so the thing is, we have some collapse, something collapsed. The image collapsed. Okay, two objects make it to be one object. So we can no longer do the inverse.
I have a question, please.
Question.
So it says, so as long as the transformation doesn't not project the vector space on a lower dimension, the function is invertible. Is this correct?
Yeah, that's exactly the idea. If the map between two vector space, now the image does not have a lower dimension, then that's invertible. Okay, as long as we preserve the dimension, then it's invertible. Good. So this is exactly the idea. So you see, if we that's exactly what I want to, the conclusion that I want to make this conclusion. So you see a trivial example. A trivial example. So for instance, okay, the matrix A is 0, 0, 0, 0. So anything I map it to 0, 0, 0 vector, J map it to 0 vector, 0, 0. Then you see anything on the XY plane, it maps to a point, map to the origin, O, origin, O. So anything on this plane mapped to it to a point O. Okay, so a plane, XY plane, the XY plane is mapped to a point origin. Okay, then we cannot invert this thing, because for a point you cannot map it to infinite many things. You do the inverse, you have many choice to make. Okay, you have many choice to make. Any point you should, it gives you a choice. So you have infinite many choice to inverse, to do the inverse. So so then this is not well defined. Then A inverse is not well defined. Okay. Exactly like the idea, for instance, multiplication by 0. Okay, for instance, real number map it to real number. A number, any number x, we map it to multiplication by 0. Then we get x times 0, we get a 0. Okay, this map f. Any number we map it to 0. So you see, once we have 0, then we see we have many choice. We have many choice, even many choice to make. So this is the f is not invertible. Because for 1, you have many choice to invert. Okay. For 0, you have many things to invert. Because multiple choice mapped to 0. Okay. Another example. If A is, for instance, 0, 1, 0, 1. This means 1, 0. This means I map it to 0, 1, which is it's just I. And J map it to 0, 1. It also map it to I. So in this case, the XY plane is mapped to anything is mapped to the x-axis. Then in this case, the dimension go lower by 1. So you see I plus j map it to I goes to I, j goes to I. So this goes to 2i. And then you see j 2i also goes to 2i. Now in this case, again, to invert the thing, you cannot define the image of 2i. So you see this the same thing, 2i. Actually, you invert the thing, you have 2 choices to make. So this is inverse is not uniquely determined. So here in this case, this map A is not invertible. Not invertible. The idea is to do the inverse, to find the inverse, to define the inverse. The target or the image should have the same direction, should have the same dimension, should not collapse, i.e. The dimension of the target vector space, target or the image, dimension of the image should be the same. If you map a plane, then you should get a plane so that you can do the inverse. If you map a 3-dimensional vector space, the target, the image should be a 3-dimensional space. Then this is the invertible, the same as that of the source vector space. The source vector space. Okay. Okay, to make sure the column, the image does not collapse to lower dimension, we need to make sure the target, the image, should be large as possible. So, i.e., you see, then here, i.e., the column. Remember, the column vectors tells us the image. Remember, the column vectors of a matrix tells us the image. Okay, the column vectors should not be a linear combinations of should be be linearly independent. It should be linearly independent. Okay. So in this case, the column vectors are not linearly independent. Then it exactly defines the same dimensional vector space as the source, as the source target, as the source vector space. In this case, the image and the target and the source, they have exactly the same dimension. So the image does not collapse. Then in this case, this operation is invertible. Okay. So we define. It's a fact, or you define it. Definition. Square matrix A. A matrix, you can view it as an operation on vector space. A is invertible. If, only if. Definition. This is definition. The column vectors are linearly independent. The column vectors of A are linearly independent. Okay. Remember, zero vector is not linearly independent with any other vector. Okay. So zero vector. So this tells us that by this definition, remember, zero vectors is not linearly independent with any other vector. So this means if a matrix has a column of zeros, then it is not invertible. Okay. So if A has a column of zeros, then A is not invertible. It is not invertible. Okay. Now we give a name of a matrix that is not invertible. Definition. A square matrix is called singular if it's not invertible. Not invertible. The idea is if it is not invertible, then the image should collapse, okay? Collapse somehow. Now this is actually a central problem to compute the inverse, okay? The question is how to determine whether a matrix is invertible, and if you have a matrix, how to determine if it is invertible. Now the second question is if it is invertible, how do we find its inverse? Okay, this kind of questions will be answered in next chapter. Chapter 2. How do we find the inverse of a matrix? How do we determine a matrix is invertible? Okay, here is the homework for this section. Homework for this problem set 1.3. This is a number 1, number 3, number 4, number 5. Okay. Okay. Now let's go to next chapter, chapter 2, solving linear equations. Solving linear equations. Okay, the problem like this. Given a system of linear equations, we want to find its solutions. Two questions, whether there exists solution or not. Next question is, if there is solution, find all possible solutions. We would like to find its solutions. Now, of course, we should determine whether there exists solution or not. Then if it has solution, then find all solutions. Okay, actually solving this linear equations, this kind of problem are almost everywhere. You know, in machine learning, most time you need to do this solving linear systems in some reasonable time. Okay, let's see this example. We all know how to do this. X minus y equal to -1, x plus 2y equals 5. Now we know from this, from algebra, how to solve these equations. Now today, there are different point of view to do this kind of problem. Now you can use, for instance, each thing is a line, okay? It's a line equation. So you can find they are not parallel. So they are not parallel. So they should intersect because they lies on the xy plane. So two lines naturally intersect at one point. So if you plot this thing, plot this. Okay, now this is not difficult. So it's 1, 2, 3, 4, 5. So x coordinate is when y is 0, y is x is 5 here, x, y. Now when I'm plotting a second equation, when x is 0, y is 2.5. 1, 2, 2.5, 3, 2.5 is here. So we get this line. So we get this line. Maybe let me insert a line. Okay, so we get a line. Okay, so we get a line. So this line is, we can find its equation. It's x plus 2y is 5. And then we have another line. So which is if you write it as y equal to x plus 1. So you can find it pass through this point, 0, 1 and -1, 0. And then you plot another line. They necessarily intersect. Okay, they are not parallel, non-parallel, so they intersect. So the intersection, they intersect at one point. This is actually 1, 2, 1, 2. Now you can actually check this is indeed the solution. You need the solution. So this is one way, and we can also write it in this form. You can also write in this form. Use matrix multiplication. So you can write as x. You see the coefficients of x. So you write it as xx plus -y 2y, which is -1, 5. Okay, so this is x, y1 plus y times negative 1, 2 is, so this becomes a vector problem. So find what the multiple, find what the linear combination of these two vectors, such that these two vectors, the linear combination get this negative 1 and 5. Okay, or you write as matrix notation. Matrix notation. Now you write it as the x correspond to the first column 1, 1. The y correspond to the second column negative 2, negative 1, 2. Multiply xy. Okay, this equal to, okay, i.e. you can have another point of view. This is the a, this is the vector x. This you get a vector b. Okay, i.e. under what transform, you get a vector b from a vector x. Okay, there are different point of view. Okay. Okay, how now, for instance, what does the vector linear combination, the point of view of linear combination? So let's do the linear combination point of view. Okay, the vector 1, 1, the vector 1, 1. So let's plot the vector 1, 1, and then plot the vector negative 1 and 2. So the vector 1, 1. Vector, suppose it's negative 1, this is 1. 1, 1 is 1, 1 is in this, suppose it's here, 1, 1 here. 1, 1 is this direction, 1, 1. This linear combination 1, 1, and another vector negative 1, 2. This 1, 2 here, negative 1, this is negative 1. We have another vector, which is a negative 1 and 5. Negative 1, 5. Let me insert some space. Three, 4, let's see, 5. Okay, all right. 3, 4, let's see, 5 is here. So it's negative 1, 5 is a vector here. Negative 1, 5 is a vector here. Okay. It's negative 1, 5. Now, the thing is, we know the solution. We already know the solution, xy. Xy, you check, very easy to check. You check the xy is 1, 1, 2. You check it works. Now, which means x multiple y multiple of this vector 1, 1. I think this vector we need another multiple. We need a multiple 2. Okay, this sum to the vector negative 1, 5. Okay, this sum to the negative 1, 5. So there are different point of view to do this kind of problem. So the idea for this problem is the column vectors are linearly dependent. The column vectors are linearly, they are in different direction, okay? They are linearly independent. I.e., they span the same, the whole space, okay? Vector C1 and C2. Here in this case, C1 equal to, let's see, 1, 1. C2 equal to C2 equal to negative 1 and 2. So here C1 and C2 span. Use linear combination is this span all whole space. span the whole space, the whole xy plane, the whole vector space, xy plane. So there exists some xy. So there exists some linear combination, some x plus y C2, such that we get exactly this negative 1.5. Okay, and then we check this actually x equal to 1, y equal to 2 actually works. Now the third point of view is transformation. We write it as A. We transform the vector x for what vector x that we transform it in certain rule such that we get negative 1.5. Well, we can use another point of view. For transformation, we know actually the columns are linearly independent. So here we know A is invertible. A is invertible. Which means because by definition, the column vectors is column vectors are linearly independent. So which means so there exists some inverse. There exists it's inverse. It's inverse. A inverse. Okay.
Sir, I have
So,
a question.
Question?
Yeah. So does it imply if we found the determinant of the matrix, we could know if it's invertible or not?
We don't define the determinant yet.
Oh, okay.
We don't define the determinant yet. So we define a matrix to be invertible if its column vectors are linearly independent. This is the equivalent. We have several definitions of to be invertible. This turns out to be, later we will see actually they are equivalent. For instance, the determinant is non-zero. So now we can actually do the inverse. Now A inverse AX is A inverse negative 1.5. Now this actually A inverse times A gives us identity matrix. Identity matrix times X. Identity times X gives us X. Okay, X. So it's A inverse negative 1.5. However, we don't know how to compute A inverse yet. In later, we will give algorithm how to compute inverse. Okay, how to compute inverse. Okay. Now more examples. Now this equation, x plus 2y plus 3z is 6. 2x plus 5y plus 2z is 4. 6x minus 3y plus z is 2. Okay. There are several different point of view. For instance, if we do the rule picture as we did it for the last time, if we have two variables, now each equation defines a plane. Okay, remember we talk about how to find a plane, how to write down the equation of a plane in the XYZ space. Okay, 1, 2, 3. The equation 1, 2, 3. They all define a plane. Okay, they are all equations of three planes. Okay, of three planes. Okay, so the rule picture says the three planes intersect at a one point. Here, if you solve it by algebra, you can solve it by algebra. You can actually find a unique solution. So the rule picture says the three planes intersect intersect at exactly one point, at one point. At one point. It's possible that if two planes are parallel, then there's no intersection. It's possible that you get parallel planes. You get parallel planes. So in that case, there's no solution. Now, what does the rule? So this rule picture says. Now, what does the column picture says? Column picture. Column picture. Column picture. Okay, column picture. Now, rule tells us plane, three planes intersect at one point. The rule picture tells us for what the linear combinations. So if you write in this form, x, 2x, 6x, plus 2y, 5y, negative 3y, plus 3z, 2z, z equal to 6, 4, 2. So this is column picture. Okay, you write as sum of three vectors, column vectors. Now, if you write this thing, you factor out the x. 1, 2, 6. And y times 2, 5, negative 3. And then you have z, 3, 2, 1, which is 6, 4, 2. Okay, 6, 4, 2. Now in this case, you see some linear combinations of the columns. You know, we get 6, 4, 2. Now you see the z, the third column vector, 3, 2, 1. You see clearly 6, 4, 2 is twice that thing. You see twice 3, 2, 1 is actually 6, 4, 2. So actually we get a solution. In this case, that's easy. We get a solution 0, x 0, 0, 2. Excuse me. So we get a solution very easy if we look at this, use the column picture. Okay, column picture. So this is the x equal to 0, y equal to 0, z equal to 2. Okay. Now let me give you a remark. You see, for the same object, we can either, for this linear equation, we can use the rule picture, which gives us the geometry of three planes intersect at one point. And then, if we use column pictures, then this is linear combinations of three vectors. Vectors is linear. It's a one-dimensional object. It's a line. Okay, this by certain vectors. Okay, this gives us two-point of view between plane and the lines. Okay, between planes and the lines. Actually, this idea gives us symmetry between objects. Okay, this gives us symmetry between line and plane. This actually, we have a principle in geometry that once you get a theorem about planes, Euclidean, like Euclidean geometry, if you have some theorem about planes, then you get a corresponding law for lines. Okay. Once you have a theorem for lines, then you can get a corresponding theorem for planes. So this idea is called duality. Okay, duality. The duality between line and plane. Okay. Now what does, of course, you can write it as a matrix. If you write a matrix, it will be looks like this. So this, the image of x. So 1, 2, 6. Now the second column, which corresponding to the y part, 2, 5, negative 3. And then the third column, 3, 2, 1. Okay, this is the matrix A. This multiplied by x, y, z is a vector. Tells us the 6, 4, 2. Okay, if you write it in this form, so this is A, the matrix A times the vector x. You get another vector. For instance, let's write it as B. Okay, so here we solve x by multiply the inverse. Multiply the inverse. So it's tedious actually to check the column vectors here. The 3 column vectors are linearly independent. So that's a unique solution. Right now we don't know how to find A inverse yet, given the matrix A. And later we will determine how do we solve A inverse. How to find A inverse given some matrix A. Okay, how do we show that actually the rule picture, for the rule picture, the 3 planes actually, how do we see that the plane actually intersect at one point? How do we actually conclude that the 3 planes, they intersect at one point? Actually, we can use the normal vectors. Okay, the normal vectors. 2 planes, geometrically 2 planes are parallel, then they have the same normal direction. Okay, so geometrically we can use 2 planes. 2 planes are parallel. We know the 2 planes should be distinct, parallel. So we assume they do not coincide, are parallel, which is equivalent to distinct plane. They have the same normal direction. The same normal direction. Normal direction. Normal vector. Not the same. Let's use parallel. They have parallel normal vectors. Parallel normal vectors. Okay, so suppose we have this plane which has normal vector n. Now suppose we have another plane which is normal vector m. So plane let's use S1, S2. S1 is parallel to S2, which is equivalent to they have the same direction, means normal vector is is a multiple of another for some non-zero, for some lambda in real number. Okay, here it's not less. We don't worry about lambda is 0 or not. Okay, because here m and n, they are non-zero. So here lambda cannot be 0. Okay, so we can use this relation to determine whether 2 planes are parallel or not. Okay. Okay, for example. Okay. Now, last time we talked about the plane equation, how to write down the plane equation once we have a point on this plane and we have a normal vector. Okay, remember? Suppose we have normal vector. Suppose we have point P. We have normal vector. Suppose normal vector is ABC. Now P is x0, y0, z0. Now any point Q on this plane, if we connect PQ, then it naturally normal is perpendicular to the normal vector n. Okay, so suppose Q, take Q to be xyz. Arbitrary point on the plane. Let Q be a point on the plane S1. On S1. Then we have PQ. Then the normal vector is perpendicular to PQ, the vector PQ. Then this means use dot product Dot product is 0. Dot product is convenient to determine perpendicular. Okay, so PQ, you see PQ, you can write down PQ. Head minus tail, x minus x0, y minus y0, z minus z0. Okay, the dot product, if you write down, it's a dot x minus x0 plus b y minus y0 plus c z times z minus z0 equal to 0. x0, y0, z0, they are numbers. ABC, they are numbers. Okay, if you distribute the thing, and you finally get ax plus by plus cz plus some numbers c equal to 0. So then you get the line equation. You see, the coefficient x, y, z gives us a normal vector. Okay, we can read the normal vector from the coefficients. Okay, we can read the coefficients of x, y, z to get a normal vector. Okay, for instance, let's see this example. X equal to 2y, x plus 2y plus 3z is, let's see, to be 6. It's equation 1. X plus let's use 4x plus let's use 2x plus 4y plus 6z is let's see 5, for instance. I think any other equation we don't care. So these are three planes. You see, now if you write the plane, the normal vector for plane 1, you can write as for plane 1. For the plane determined by equation 1, what is this normal vector in 1? Normal vector for plane S1 defined by equation 1. Okay, now N2 is determined by S2 equation 2. Now N3 we don't care. Okay, so what is N1, N2? You can read the coefficients N1. You can choose, for instance, 1, 2, 3. Just look at the coefficients of the equation 1. Coefficients x, y, z in equation 1. Then you get a normal vector. Now N2, what is N2? N2 is 2, 4, 6, which is a multiple of 1, 2, 3, which is twice N1. You see, then the vector N1 and vector N2, they are parallel. Okay, so this means equation 1. So this means S1 is parallel to S2, which means S1 intersect S2 should be empty. No intersection. Then this has no solution. This means the equations has no solution. Have no solution. The system of equations. The system has no equation. No equation. Simultaneous equation. No equation because there's no intersection. Because two planes are parallel. Okay. Okay, so they are parallel. They are not coincide. They do not coincide. If they coincide, we just delete. This is redundant. Okay. So in this case, they are not coincide. They are parallel. Okay. Okay. Another idea. Example. Okay, let's see this equation. Let's see this equation. How do we determine whether this solution, this equation has solution or not? Okay, here we use the now if you use rule picture, you don't see the planes. You don't see the planes are parallel. They are not parallel. In this case, is there still intersection or not? Is there intersection or not? Now, if two planes intersect, then we get a line. Now, it's possible that the intersection, this line, has no intersection with the plane. Okay. So, equation 1, 2, 3. Now, it's possible that equation 1 intersect equation 2 gives us, now equation 1 intersect equation 2. This gives us a line and a plane. So suppose we have a plane. What's the relation of a line and a plane? It's either parallel to this plane or it intersect. Or this thing lies entirely in this, or this line lies in this plane. Okay, lies in this plane. 3 possible cases. So this actually the rule picture tells us. Now actually let's see the column picture. Now it's hard, it's not easy to determine whether we have a solution or not without algebra, not solve it directly. But if you do it in this form, the intersection is a line. Now, if you do equation 1 plus equation 2, what do you get? Then we get a 2x plus x, we get 2x. 3y plus 2y, we get a 5y. 5z plus 3z, we get a 2z. Then 5 plus 4, 4 plus 5, we get a 9. Now this is a contradiction with 3 because 3, this is actually it. So that we see these two planes are parallel. So there's no solution. So we can conclude the contradiction tells us there's no solution. I.e., which one do we have? Which one do we get? Actually, we get the case that the line, the intersection of equation 1 and 2 should be parallel with plane 3. Okay, with plane 3. So this is what we get for the rule picture. Now column picture, what do you get? If you write column picture, you find what columns that do we have. Okay, sorry, the OneNote is okay, it recovered. Okay, what does the rule picture tell? The rule picture tells us, we already know what the rule picture tells us. Now let's see what the column picture says. Okay, let's see column picture. Column picture, you write it as X component 1, 1, 2. Y component. You read the coefficients of Y.
We can't see your screen anymore.
Oh, sorry. Okay. What happened? Jesus. Okay. Okay. Now it finally works. Does that work?
Yes.
Okay. Okay. Now it is work. Okay. Let's see what the column picture tells us. The column picture, you read the coefficients x, y, z. So the column for y corresponds to the second column. You read all the coefficients of the y in the equations, 3, 2, 5. Okay, and then you read the coefficients for z, 5, -3, 2. Okay, this you get 4, 8, 3. Okay, so some linear combinations of these column vectors we want to spine. We want these column vectors, column vectors spine this 4, 5, 8. Is that possible or not? This is actually not possible. We already know there's no solution. So there's no such linear combination. Now the thing is, the 3 column vectors, so this is C1, this is C2, and then this is C3. The 3 column vectors, they are coplanar. They lie on the same plane. The 3 vectors, they lie on a plane. Why? Because if you take this n to be 1, 1, -1, so you see n dot product with C1. This will be dot product C1. What do you get? You get a 1, multiply the thing. So you get a 1, 1, -1, multiply 1. Dot product is 1, 1, 2. So this you get 1 times 1, you get a 1, 1 times 1, you get a 1, 1 times -1 times 2, you get a -2. So you get a 0. So n is perpendicular to C1. Similarly, if you check n dot C2, then you get the same thing, you get a 0. So it's 3, 2, 5. So you get a 3 plus 2 minus 5, which is 0. And n dot product with C3, you get a 1, 1, -1. Dot product with 5, -3, and 2. Then you get a 5, -3, -2. Then you get a 5 minus 5, 0. So you see C1. So the picture looks like this. This is the normal vector n. Now C1, C2, C1, C2, C3. They all lie in a plane. Okay, C1, maybe C2, C3. Okay, i.e. the 3 vectors, they are coplanar. However, the C1, C2, C3 lies in this plane. However, the vector 4, 5, so any spine, okay, any linear combination of these 3 vectors, C1, C2, C3, cannot escape the plane, okay, cannot escape the plane. Cannot, this is origin O. Any linear combination of this thing does not escape this plane, okay? So that any linear combination should again lies in this plane, and also n is, perpendicular to that. However, if you n dot product with the vector b, the vector b, 4, 5, 8, you see you get n. This is 1, 1, -1 dot product with 4, 5, 8. Then you get 4 plus 5 minus 8, which is 1, which is non-zero. So which means the vector that b here, b is not in the plane. B is not in the plane. Not in the plane. Spined by C1, C2, and C3. Actually, we only need to suffice to use only 2 of them to spine this plane, because the three are coplanar. So B is not in the plane. So B is not the linear combination. So B cannot be a linear combination. Linear combination of the three column vectors. Column vector C1, C2, C3. Which means no solution. The system has no solution. Okay. And this also, of course, this means A is not invertible. So if you write this thing AX to be B, now this means A is not invertible. A is not invertible because if A is invertible, so you can multiply it, you can get inverse, you can get a solution. Okay, A is not invertible. Okay, A is not invertible. This also follows from definition. Remember, we define a matrix to be not to be invertible if the column vectors are linearly independent. However, the three column vectors C1, C2, C3, they are linearly dependent. Okay, they are linearly dependent. They lie in one plane. So in this case, A is not invertible. A is not invertible. Okay, any questions? Okay, example. Example. X plus Y plus Z equal to 2. Equation 1. X plus 2Y plus Z is 3. Equation 2. Equation 3. 2x plus 3y plus 2z is 5. Equation 3. Now, we want to find this solution. How does the solution to this equation looks like?
No solution.
Let's see. So, you know, in general, so the rule picture says, the rule picture says, you know, this is the intersection of 3 planes. Okay, 3 planes. Now, if 2 planes are not parallel, then they intersect. Okay, so here any 2 plane, any of the 2 planes, they are not parallel. You can see they are not parallel. The normal vectors, so the normal vectors are not parallel. The 3 normal vectors, n1, what is n1, n2? Normal vector is 1, 1, 1. n2, normal vector is 1, 2, 1. Normal vector n3. So they are pairwise, not linearly independent. 2, 3, 2. You know, any vector n is not a multiple of another. Okay, so they are not parallel. So this means the 3 planes are not pairwise parallel. Okay, none of the pairs. Okay, 1, 3, 2, 3, 1, 3. You know, the 3 pairs is not parallel. Not parallel. So, so 1 and 2, they intersect. They are not parallel. Then they naturally intersect at one point. Intersect at one line. Okay. So equation. This is let's see. Suppose this is a. Let me plot the picture. So equation 1 and equation 2, they define the intersection of 2 planes. They are not parallel. So this means we should get a line. So the intersection is a line. So the intersection. So let me plot the intersection. Plot the intersection as a red line. Okay, let me plot, use another color. So so the intersection is this. The intersection is, you know, the line. Is a line. Now, the intersection of 1 and 2 is a line. Now the next question is, what's the geometric relation of this line with another plane? Now we have three cases of a relation of a line and a plane. Either they can be parallel. You see here the three cases. They can be parallel. The line can also lie in this plane, or they intersect at one point. Okay, so these three cases. Now we need to determine the relation of this line with the third plane to see how this geometrically the intersection looks like. Okay, so now you see suppose we have a solution, equation 1 plus equation 3, equation 1 plus equation 2. What do we get? Equation 1 plus equation 3, what do you get? Equation 1 plus equation 3. Then we get...
You get the same as equation 3.
Equation 3. We get the same thing as equation 3. So if a solution XYZ satisfy, you know, the intersection of 1 and 2, satisfy equation 1 and equation 2. So if we add them, then you see we see XYZ satisfies equation 3. So this means XYZ, the intersection XYZ, a point, intersection, a point of S1 intersect S2. So suppose this is the plane S1, this plane S1, S2, okay? So the intersection is a point XYZ, so P. So which means P satisfies equation 3. So which means because P is arbitrary point, okay, P is arbitrary point on this intersection, which means the line L, which is S1 intersect S2, lies entirely in the plane S3, defined by equation 3. Okay. So what is the set of solution is? So what's the solution set for this equation? What's the set of equation? What's the set of a solution to this equation? What's the solution set? Anyone know? What's the solution set? The solution set should be a line, okay? So the solution set, the set of solutions to the given equations forms a line, okay? Forms a line. Now how do we determine the line equation? Now we need 2 points to determine a line. Now actually we determine the line equation so that we can determine the solution set. Now remember, we need 2 points to determine a solution. You see, to determine this line, we only need equation 1 and equation 2. Or you use equation 1 and equation 3. Or you use equation 2 and equation 3. So let's suppose we use equation 1 and 2. So we just solve equation 1 and 2. solve equation 1 and 2. X plus y plus z equal to 2. X plus 2y plus z is 3. So 1, 2. So we solve the thing. So for instance, we find a solution. There are many solutions. For instance, if you take z to be 0, so you get x, y plus y is 2, x plus 2y is 3. So it's easy to solve. X is 1, y is 1. So if you take z to be 1, then you get x plus y to be 1, x plus 2y is 2. So you get x is 0, y is 1. So you get 2 points. So you get 2 points. 2 points. 2 points. Which is the 1, 1, 0, and 0, 1, 1. Okay. Use 2 distinct points, we can determine the line. Okay, uniquely determine this line. So if you have this is a point P, this point is Q. Now to determine this PQ, so use the direction, this direction. Okay, direction vector PQ. Direction vector PQ is Q minus P, head minus tail. So it's a -1, 0, 1. Okay. Now any point, suppose this is the R, X, Y, Z. Now you see we have PR should be lambda PQ, should be lambda PQ in the same direction as PQ. So you get a solution. You get so it's X minus 1, Y minus, sorry, you need a P, the coordinate of P, and Z, which is lambda PQ, -1, 0, 1. So you get simultaneous solution, X equal to X minus 1. Compare component, Y minus 1 equal to 0, Z equal to lambda. So the solution set is X to be Y minus lambda, Y is 0, Z is lambda. So lambda can be any real number. So this gives us the solution set. Okay. Now we don't have time for the matrix picture. Now remember, if we maybe we just briefly mention it. So if we write a matrix picture, remember if we have A is invertible, then we can do the inverse. So that we get the unique solution. X is A inverse B. But here we don't have a unique solution. This means A is not invertible. A is not invertible. A is not invertible. Okay. Now you see the rule picture tells us why is A not invertible? Because if you look at its rule pictures, we already know it's not invertible because it has a more than one solution. Okay. So we can get another conclusion. If the rule vectors are not linearly independent, then the matrix is not invertible. Okay. If you look at the coefficients, the three normal vectors, they are not linearly independent. Then we know the matrix A is not invertible. Okay. So we get if the rule vectors are not linearly independent, then A is not invertible. Actually, A is invertible only if the rule vectors is linearly independent for square matrix. Okay, we will later show that. Okay, maybe it's a good time to stop here for today.